If no, I don't believe you, but that's okay. Shoot. Oh no. Okay, this is a very exciting part. So nothing from homework stuff? Why am I having so much trouble? There, it's plenty. Yes. 9 from 310. Oh yeah, we still have to finish up. Is that the one you're asking me about? Yeah. Okay, let's do that. If that's the only question, I'm going to answer that question with a different example here in a bit. Okay. Yes. Yes. 3-6, number 30. Today's lesson brought to you by Optometrist of America. Come on. Where's 30? There it is. Dominate. Raw. Okay. That one? Yes? Okay. So you guys, help me out. What would I do on number 30? Could I cancel these? No. Thank God, no. Well, you wish you could, but no, we can't. Yeah, you pretty much should do quotient rule. I mean, you could bring this up to a -1 power, but to be really honest, don't follow young Jeff's footsteps. That's kind of silly. Did you try to apply the quotient rule and it got trippy? Okay. What's the derivative of ln x again?
1 over x.
So it'll be derivative of the top times the bottom minus the top times,
The derivative of the bottom.
and what would the derivative of the bottom be?
ln x, 1 over x.
Well, derivative of the bottom is just going to be 1 over x, yes? Is that cool? All over
The bottom squared.
bottom squared. And away you go and whatever, okay. Did you get to that point? Okay. So the great thing is if you distribute 1 over x, you'll see something cancel wonderfully. You'll get a positive ln x over x minus ln x over x. Do you see that? Yeah. Yeah, that's it. I think that's all I wanted from you, right? Was just to find the derivative. You still look.
You wanted to find the derivative of it a second time.
Ooh, okay, second derivative. Ooh. So here you would get. Is everybody cool with positive minus? They cancel, so I'm just left with 1 over x on top. So I can write that like this. Is that okay? So 1 over x minus 1 over, plus 1 over x ln x minus 1 over x ln x. Cancels. All over blah, and I can just pull the x down. And then you want to take a derivative of this. Yes? Now this, do you see how the top is a constant? You with me? If that's true, I'm not going to apply quotient rule because what's the derivative of the top? Well, I could, but the derivative of the top is 0, correct? So it'll be 0 times who gives a shit minus the top times the derivative of the bottom, and that's where all the work lies, yes? The bottom is a product with a quotient, the product with a chain. So what was the second derivative you had trouble with? Okay. So you, if you do quotient rule on this, that's fine. It's just that derivative is 0 times who cares, minus the top times the derivative of the bottom, and this is basically where all the work is going to be, yes? That derivative is a chain with a product with a chain. Which is now, maybe less things on there. So I'm not So if you got to that point, you're doing pretty well. Yes? So maybe there's a specific problem that happened after that you can show me later. Is that okay, guys? Did anyone else try this problem out? Yet? Okay. Did you get to that point? Yes? And then hopefully beyond. Sort of. Okay. Alright, here. Let me stop writing on the board because that looks terrible. Let me copy down what we got to here. Don't worry, I'll show you what I'm writing here in a minute. Are you dying? Oh, man. Okay. No, Jeff. Okay. So we're here. Okay. Let me erase all that business. Okay, I am zoomed in. So that's the first derivative, yes? There's an argument to be made that you could rewrite this like this and then just attack that. Do you guys see that? Or you could do quotient rule, where quotient rule, the first thing has a derivative of 0, yes? I don't know if you guys are with me at all. So it's up to you. Quotient rule, especially when the top is a constant, you don't have to do quotient rule. It just doesn't make sense because part of it would be 0 anyway. You can just bring the top up and then just attack that directly. Are you guys at all with me? So I don't want to say anything else because I could have given you this function first and just said find this guy's derivative. What would you do? Product rule, yes. And then within that you're going to have a chain rule and blah, blah, blah. Okay. The thing that is surprising me that nobody's asked me about is if I have a function like this. No, this is fine. I kind of like that nobody's asked me about this. I almost don't want to bring this up. But do you guys see how this is, what are you doing there? Do you guys see how this is 4 times x times sine x? So you can think of it as 3 functions, but that's silly to do because you would do 4 prime x sine, but what's 4 prime? So that term wouldn't show up anyway. So these ideas of constants being parts of things, their answer won't show up anyway because they would make the whole thing 0. Does that make any sense? That's why we look at this as 4x times sine x and just do those. Because the 4 wouldn't contribute anything. Okay. Just in case that was like on the edge of somebody's brain. So hopefully that's enough to kind of help you try the next step. You could rewrite it like this, or you can keep it like that. Or you can erase it and hope I don't notice. No. Anything else, guys? Homework stuff or anything? You guys doing homework? Good, okay? Okay. Let me see. Let me catch up. Did anybody else come? Kehlani's not here. Sidrak? And Galilei? Okay. All right, guys, so there's a question kind of laying out there. Somebody asked me, and it's going to be incorporated into what I'm about to do. We're going to review section 310. I'm going to finish 310. We haven't finished 310 yet. We barely had any time in 310 last time. And then we're going to get into chapter 4. Are you guys feeling better about like chain rule stuff? Yes, it's all about practice. It's really all it is. And the hard thing is, a lot of mathematics, not a lot of it, but there are some subjects that like, it just has to click. It just has to click. And how do you make that click come? You look at a lot of different problems. So a lot of it's kind of like brute force, just force it in your brain, but sometimes it's just, you gotta do enough and then something clicks and then you look at it right. You look at the problem right. And I don't know if you guys have ever experienced that before. And then you're like, I can do any of those problems now. Sweet. Some of you guys are like, that would be great if I could feel that way. It'll be there. And this is why I assign the homework that I do. But just to reinforce what I said earlier about homework, if you can't finish it, don't. Don't leave entire sections untouched, yes? But when you do some problems, don't do only the odd problems and get them from somewhere else. Be very careful about that, yes? Get a mixture. You want some problems without a safety net, because you're not having a safety net on the test. You guys know what I'm saying? We have a safety net for odd problems in the back of the book. Okay. So let's get back into what we were doing last time. In fact, let's look at a specific function here. You could do it, Jeff. Let's do 3x minus 5, sure. I want to make it that gross. No, let me change that. Let's just do square root of x plus 1. There we go. Much better. Okay. We'll get the gross ones here in a bit. So they're going to give us a function. They're not going to ask us this question, but we know we're going to translate what they ask us into this question. Find the linear approximation. This is what they're going to ask us. To f of x at x equal to 3. Does somebody know how to translate that into less freaky calculus? Not quite English, it's just less freaky calculus. Find the tangent at 3. Yes? That's all that means. So again, I know I've said this before, this section is nothing new. This is just, oh, remember those tangent lines you made? You can do shit with them. Who knew? So can you guys help me? What are those first steps to start to find? So that's the question in our translation. You point Google Translate at it. Say, Google, translate this to less freaky calculus. And it says, find equation of tangent line at x equal 3. Okay. Did I get to tell you guys I write equation like this? I told you that, yes? Okay. I do it without thinking about it, and then people later are like, what the shit's that? Oh, yeah. Okay. So help me out again, I'm sorry, what's the first step? Find the derivative. So you guys take a moment and find this function's derivative, don't say anything. Some of you guys have done that already. You're like, wait for you to catch up. All right. What's a good first step to get there? Anybody? Kick ass. So what's the derivative?
1/2 x plus 1.
And if you wanted to, you can rewrite that as 1 over 2 square root of x plus 1. Right, the negative 1/2 means it goes on the bottom. It's a 1/2 power, so it becomes a root. The 2's on the bottom, so it just goes down there with it. Is that okay? Do you have to rewrite it like that? Hell no. In fact, you guys know how I feel about radicals, but you could rewrite it like that. That's fine. How do I get the slope, though, that I need? Plug in 3, because this tells me the slope everywhere. I don't give a shit about everywhere. I just care about 3. So what do you guys get when you plug a 3 into that? Yes, you get 1/2. 1 over 2 times square root of 4 is 1 over 2 times 2 is 1/4. Is that? Okay. So we got the slope. What else do we need for the equation on the line? A point. And we know the input is 3. I just have to get the output. We're going to shove 3. The original equation, kick-ass. Because the original equation's job is to tell you where the function is. The derivative's job is to tell you how it's moving through that point. Yes, maybe. And very soon we're going to actually talk about what does the second derivative mean graphically. Yes? Okay. Not quite yet. So what point does this go through? 3 comma 2. Because when you plug a 3 in, you get the square root of 4. So the point is 3 comma 2. So can we take this information and get the equation of the tangent line, which is also called the linear approximation? Just trying to type up the language. Huh? No, I'm just waiting for people to do it. Let's see. A few people are writing, so that's all it takes for me. Everybody else is got like somebody else is doing something. Yes, yes. So if you want to, there's nothing wrong with doing the process where you solve for b. If you know what I'm talking about, you can do that. If you don't know what I'm talking about, you can just do this. So y minus 2 equals 1/4 times x minus 3. So I get y equals 1/4 x minus 3/4 plus 2 is plus 5/4, yes? Okay. So before we would find that, we would make the graph, we would go, ooh, look, and then we would, that's it. So now we're finally saying, hey, that tangent line, it has a lot of uses. And I need you to understand, if you take Calc 2, you will expand on this and improve the approximation using higher derivatives. Do you see how this one uses the first derivative? And it becomes a decent approximation, but not for very far. If you use the second derivative in a way, you can go further. Third derivative further. If you use an infinite number of derivatives, you can sometimes make it exactly right. I said too much. That's Calc 2. Don't worry about that now, I'm sorry. So what is that line's job? What does it do because of how we built it? That's a weird question and I don't seem to care.
It will give you outputs for points around 3.
Yes, if I use inputs close to 3, it will give me outputs close to the right output. Okay. So let me give you a question the way I would put it. I want you to, what was the original function? This. Yeah, so let me copy down. Has everybody got all this business? I've been talking long enough, I think everybody got that. So let me put down what we found. Given this function, we got this linear approximation. Let me use L for linear approximation. And it's going to be around x equals 3. So how would you estimate, you can do it, Jeff, the square root of, can you do it, Jeff? Maybe. Yeah. 4.4. 4 point, hold on. 4 point, I can't think this morning, hold on. Yeah, 4.2, there we go. I'll get there something. I want to estimate the square root of 4.2. Do I plug 4.2 in? No, because what was my function? So here's the idea. If I want to estimate the square root of 4.2 using what we just did, I have to first figure out what value of x would give me that in the first place. So our function is x plus 1 inside of a radical, yes? So what would I make x to end up with the square root of 4.2? So if you want to look at it algebraically, I want 4.2 to be x plus 1, because I want the inside to be 4.2, yes? So then what's x? 3.2. Is 3.2 close to 3?
Yeah.
Part of what we're going to talk about Sure, Jeff. Part of what we're going to talk about in a minute is what's close enough. Do y'all agree with me the square root function is a nice function? It's not like, it's, so I could go actually pretty decently far away and it still is a decent approximation because my function is calm. We call it a well-behaved function. So is everybody, I need you to understand, don't just blindly shove the number in that they give us. What does x have to be to make that true? Because what is this function, this needs the value of x. So if I make x 3.2, I get what they want me to estimate. What can I do with 3.2 now? Plug it in. So what do we get? Let's see. I purposefully made this something you could do without a calculator. What's 1/4 of 32? What's 32 divided by 4? So what's 3.2 divided by 4? 0.8. And what's 5 divided by 4? That's right, kids. And so what do I get here? 2.05. Now, can somebody in your calculator, what's the square root of 4.2? We know that's not right. The answer we got is not right. But it should be decently close. 2.049. Holy shit, yes. I kind of knew it was going to be that close. Again, well-behaved function. So I can go relatively far away. Are you guys kind of with me at all? The power of this is the here the original function was. It's going to be so much less complex if I use a tangent line approximation, especially if what I'm doing doesn't mean exact answers. Yes? Is everybody with me? So that's a full-blown find linear approximation and then use it. Okay. So then the question becomes, all right, Jeff, all right, math boy, how far can I get from 3? So can one of you guys, so how close we were we? It was 2.049 what now? Sorry? Do you have it still up there? 3.9? Okay. So we were 0.0006 roughly away. 0.0006. Are you with me? Our output that we got, our estimate, was off by 0.0006. That's pretty good in most applications, yes? Okay, I like it. So what if I wanted to know, okay, how long is what would my x's have to go? You guys know this. What would delta be? So that epsilon is at most 0.01. That little delta got way excited. Sorry. Okay. I can use that language. The last time I taught calc, I actually had to skip 2.4, and you're all like, you could have done that again. 2.4 is we were talking about epsilon delta. So now I can just say that shit. You all should know. So when I say delta, that's how close can I get on the x-axis to my inputs. So that in epsilon is, so that my outputs are within 0.01. Now we got 0.2 away from 3, are you with me? We got 0.2 away from 3 and our output was within 0.0006. Yes? So it feels like I could go pretty far away relatively and still stay within 0.01. Because we went 0.2 away, we were well within that. Are you guys getting the gist of what I'm saying here? Okay. This is not something you can calculate on paper, at least definitely not easily. So here's the idea. I want, in fact, just to show you, where'd it go? Oh. One thing you need to really love is that you have a book that has examples. You see how this is basically what we're doing right now? So if you are stuck on a problem, please feel free to ask me no matter what, but the very first thing you should do is there an example like this? I think I told you the horror story about you get high enough in math and you get a book that has no examples. You're like, oh good. Okay, so here I want this function, where'd it go? Jeff, you can do it. I want this function, where'd it go? To be less than 0.01 away. I gotta remember, oh yeah. I want the difference between my original function and our approximation, which was, there it is. So I want the difference between our original function and the approximation function. I want it to be less than 0.01. Does that make sense? In fact, let's do this right now. A visual might help. So everybody got that written down so far? Did you sign in, Jeff? I did. By the way, before I forget, real quick, before I forget, I just want to show you, what was the, something like sine y plus x squared equals e to the 4y or something. Look at, all right, real quick. All right, this is not the complete picture. Do you guys understand what I just did? You can go to Desmos. Can your graphing calculator do this shit? No. That $100 and whatever thing can't do the shit, but this free thing online can do it. Do you understand what I'm doing? That is not a function. Now watch this. Do you guys, this is trippy already, yes? Do you guys agree? This is trippy already. Actually, let me say this better. Is this a function?
No.
Doesn't pass the vertical line test, yes? This is a relationship. And I know it's not a function because I can't solve for y. But it's even trippier than you think, because can you see down here at the bottom? Can you see that little thing? Now watch. Teardrops. Yes? Isn't that trippy? And now one thing Desmos can do is if I put an A instead of the 4 up there, I can make a slider and I can show you what happens if I change the power. Okay, that's trippy, yes? That is exceedingly trippy, niftedelic. And this is one reason why you're not gonna have to graph that by hand, because making a table of values where the x and y is all mixed, forget about it. You don't wanna do that. Are you guys at all with me? So if you're near a computer when you're doing this homework, especially the implicit, you can graph the damn thing on Desmos, just to see what the shit it's doing, yes? It's gonna be doing some nifty stuff. Okay, Jim. So let me do this before I just did that out of nowhere. What was our function again? Square root of 1 plus x. Oh, x plus 1, I'm so sorry. And then our approximation was 1/4 x, Jeff, plus 5, of course, okay. So you can see, I mean, this is our original function, of course. And our approximation hugs it for a good distance here, yes? Now, okay. Can you see how the two start to diverge, yes? So what I want then is I want the difference between these two functions to be less than what did it say? 0.01. And so here's how you get that. And I could do this, let me do this on the graphing calculator, because you're not going to necessarily have Desmos. Let me do it on the graphing calculator. Okay. If I work with this a little bit, and you guys know how to do this, forget all the shit in here. I got the absolute value of stuff is less than 0.01. How can I rewrite that? If this has got to be closer than 0.01, it's got to be between what and what? Do you guys remember? Negative 0.01 and positive 0.01. Yes? So I want the difference between these two to be between these values. So if I want you to be at most 2 feet away from me, do I care if you're over there? No, I just want you to be within 2 feet of me, yes? And if I restrict myself to 2 dimensions, I want you right there or right there on either side of me. And that's why there's a negative and there's a positive. Give me a number that's 1 away from 3. Down, it's -1, correct? That's the one saying, oh, if I go down 0.01, I'm still within 0.01. That's why I got a negative point on one side and a positive point on one side. Okay. And then you do this. We're not going to do a lot by hand, by the way. This is the last step we're going to do by hand. I'm going to add this to both sides. Jeff, if I could write, that would be amazing. And you're all like, hell yeah. And I forgive you. So all I did was I took this and I added it to both sides. Okay. So does this make sense? I want my function to be 0.01 less than my output or 0.01 more than my output at most. That's what that says if I read that in English. So then what do I do with that, Jeff? No, well, you don't do any more work. Don't square, because that makes things really trippy. In your calculator, come here, glasses. I'm going to put these in one at a time in order here. I'm going to put y equals, clear this other weird shit that's going on. 1/4 x plus 5/4 minus 0.01. Bam! And then I'm going to put square root of x plus 1. And then I'm going to put 1/4 x plus 5/4 plus 0.01. Thank you for that play-by-play, Jeff. Okay. So what this is going to look, well, let's just see what this looks like. Is everybody with me? So I just put each side, that left side, the inside, and the right side, I just put them in each one at a time. And what I want to do visually is I want to catch this within these. So look what that looks like visually. Let's see, graph. Okay, and if you need to hit zoom 6, so you get like a -10 to 10, -10 to 10. So that's one, that's the floor. There's my function, and then the ceiling comes in. Now, real quick. I have done bad things here. I don't know why I picked 0.01. Can you see the separation between the floor and the ceiling? No, because they're 0.02 apart, correct? So here's one of my favorite buttons that exists. Where is everything basically happening is right around 3, correct? So here's my favorite button on this calculator. Besides 1, okay? Zoom box. This is the CSI enhance thing. So when you do this, let's just do this. I'm gonna hit enter, and if I move up and over, it's gonna open this box. And when I hit enter now, it's gonna zoom in on that spot. That's like the enhance. And magically the computer can do it. You guys got it with me? Anybody ever used this before? Zoom box? So if you hit enter, that's one corner of the box, and you hit over and down or up, and that makes the whole box. Now if I hit enter, there's the floor, there's the function, and there's the ceiling. Now, you could see it a little better this time, but still. So I do zoom box again. Where is everything happening is right in here, yes? Okay, god damn Jeff, why'd you do this? We'll be okay. Zoom box. So it looks like the red line enters down here. So I'm going to go a little bit down and before it and hit enter. And then I'm going to go up over here to about where it looks like the red line leaves. Okay, let's see. This probably still isn't good enough, but we'll be okay. Floor, function comes in and goes out. Ceiling. Yeah, Jeff. Good Lord, dude. Okay, so let's do this. Let's salvage this. I have chosen to be way too restrictive. Can everybody go here and make this 0.1 instead of 0.01? Are you guys with me? Just so we don't zoom in for like 50 more times. So now if I hit graph, there's the floor. There's the function. Oh shit, now I've gone too far. Damn you, Jeff. And there's the ceiling. Alright, I have to start over. Zoom 6. Okay. Floor, function, ceiling. And now I'm gonna hit zoom box. Floor. Function. Ceiling. All right, so here's the idea. Can you see that that red line is within 0.01 of either side from there to there, yes? Now, for this function, it happens to only cross one of the two walls, yes? But you could have a function that comes in and goes out this way. Okay. Let's see if you all agree with me that whatever that point is right there, it's got an x value? So that's the x value that it enters, that it gets within that close, and this is the x value that it stops being that close. Okay. So how many of you guys have ever done the intersection function of this calculator? So if you hit second trace, get to calc, and I want to calculate an intersection. I want to calculate the intersection of the blue line and the red line. So I've got my cursor like about where they intersect. So if I hit enter, it actually, do you see how it bounced to the red function now? So the first thing it says is what's the first curve? So I hit enter. Then it bounces to the next curve in my list. And that's the next curve, that's the curve I want. Yes? So then I'm going to hit enter. I'm going to tell it, yes, that's the second curve. And then the last question it's going to ask is, what's your guess? And I already put my cursor on the guess, so I just hit enter again. So it looks like starting at 0.87, oh, blah, blah, blah. If I use inputs from 0.87 to whatever this is, I'm going to stay within 0.1. I changed it so I can see it. If I use an input below this, aren't I further away? Isn't my approximation further away than I wanted it to be? Okay, maybe. So 0.87 up to. What was the best part of today? It was watching this guy just push a button. It was great. Okay, enter, enter, enter. So 5.93. That's a huge, now of course I changed the size of the error I wanted, but still 0.1. Would you all agree that if I'm within 0.1 for most everyday things, that's pretty damn good? Yes? Maybe? If I were estimating the cost of something and I was off by 10 cents, that's really good, unless it's like the cost of an eraser or something, you know, stick of gum. So I could be anywhere from 0.87 all the way up to 5.93, and my output is going to be within 0.01 of the right answer. That's what that means. Why did I have a relatively huge interval that I could live within? Two things. Really well-behaved function, and I only made it 0.1 that I had to be within. If it was 0.01, it's going to definitely get shorter. Okay, let me stop for a minute. That's probably the trippiest thing you have to do in this section, because the tangent line stuff should be old hat. Okay. So again, you got an example to kind of like have a template as to how to do this when you hit it in the homework. Okay. Yes.
Just for the graphing calculator, how do you zoom out from this point now, like for the next time?
Oh, you hit zoom 6. That's your refuge. Zoom 6 takes you back to -10 to 10. -10 to 10. That's a really good window to kind of like start in. So anytime you're trying to graph something and it just looks exceptionally weird, just hit zoom 6 and it brings it back to this. -10, 10, -10, yes. 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 Okay. If I use inputs within those, my output will be off by at most 0.1. Okay. All right. that is that. There are two more ideas in section 310. Do you guys remember I talked about this notation here? Yes? So let me see if you guys cool this. If I have a function and I want to know how much does delta y change if I change x by delta x. How much does the output change if I change the input by some amount? Does anyone remember what that triangle is? A Greek delta. Do you remember what that means? It's not change in something, but a gross change. Not meaning ooh, but meaning big. Yes. And a big change is 0.00001. That's a huge change because it's relative to an infinitesimal change. Yes? Because what's the other letter I would put there when I go to infinitesimal change? D. That's when you get your infinitesimals, your derivatives. Yes? So let's say that I start here and I go here. This is nothing major, by the way, at least not yet. This would be y, or let me say even better. This would be f of x, and this would be f of x plus delta x. Yes? So I need you to understand. So if I have an x and I want to go by delta x, okay, that would be x plus delta x. So the output for x is f of x. The output for x plus delta x is f of x plus delta x. That's amazing. What would delta y be then? How much did the outputs change? What were the outputs? F of x plus delta x, and how much did it change then? You would just do the what? What would you do to these two? If this was 7 and this was 6, how much did the outputs change? By 1, yes, so we take the difference. So how much did the outputs change? They changed by f of x plus delta x minus f of x. On one level, that is just freaking silly. How do you get how much the outputs change? You subtract the output. Oh my god, that's amazing. Okay. That is a change in y, and I can't remember what this book necessarily called that. I'm not sure if they call it something. No, it's just a gross change. And then you get the idea of a differential. So this is the actual change in y, yes? And now I want to use the derivative to approximate how much it changes. So listen to me, guys. If I told you the slope of a function was 3, write that down. If I said the slope of a function at a point is 3. And I go one step up on the x, what would you predict the y would do? Increase by 3, because that's what the hell slope means, Jeff. Good job, that boy. Now here's the problem though, is that the actual output? You just add 3 to wherever you were. No, because the instant you move to that point, the slope could change. So that is the perfect approximation if it was a straight line. But if it's not a straight line, it could curve away from that, and it will. This is exactly how much y changed. Yes? Because I look at one output minus the other output, I see how much it changed. Ooh. The differential. So help me out. What's another way to say dy dx? How do they write it? Oh, good. What's another form of that?
F prime of x?
Yes, f prime of x. Kick ass. Or y prime if you want to. Yes. Can you solve for, do you see how this is solved for delta y? Can you solve this one for dy? What would you do? How do you get dy by itself? Multiply by dx, yes? Now if you think about it, it's exactly what you guys just did. I said the slope was 3 and I went by 1. What was your prediction as to how much the y would change? 3 times 1. If the slope is 3 and I go 2 steps up, What's your prediction for what the outputs are going to do? I gotta breathe. Okay. So what's slope of 3 mean? Slope of 3, what's it mean? For every step of 1, I go up 3. So if I step 2, I'm gonna go up 6. And that's all this dumb thing says. If the slope is 3 and I change x by 2, 3 times 2 is flipping 6. Do you see that? That's all that dumb thing is. You with me? It looks trippy, but it's not a big deal. Maybe? So, the kind of problem I'm gonna give you. Here. Let's look right in the homework. Here we go. Well, here's a very in-your-face problem. Especially when I do that. Find the differential dy and evaluate dy for the given values of blah, blah, blah. So this is neat. I love this, and I want to make a big deal of this right now. You could do this 2 different ways. If y is e to the x over 10, what is dy dx? Oh boy. Don't overthink it. E is great, right? E's our friend. What's the first step for the derivative of e to the whatever? It's itself times 1/10. The derivative of the inside, yes? If I multiply the dx up, that is what we call the differential. So if they tell me, I want to know what dy is, if dx is 0.1 and x is 0, you just plug that shit in, yes? I want to know what dx is, what dy is, if dx is 0.1 and x is 0. So what do we get? 1/10 e to the 0 times 0.1. So everybody looks pained. You all look pained. Was that difficult? No. Multiplying by dx, was that difficult? No. But if I do that, we call this the differential. This is what we call it. So if they tell me, oh yeah, dx is 0.1 and x is 0, what's dy? Well, I just got to plug that stuff in, yes? So what is 1/10? What's e to the 0? 1. What's 1/10 times 1/10? 100. Now, somebody help me out. What is e to the 0? 1. Holy shit. What is e to the, now change x by 0.1. What's e to the 0.1 divided by 10? Can somebody do that in your calculator? What's e to the 0.1 divided by 10? Do it again. 1.01. So it changed by about 0.01, yes? Is it exactly 1.01? No. 1.01. Yeah. But it's roughly 1.01. All right, I need you to see this. What's 1/100th as a decimal? 0.01. So we predicted that the output should change by about 0.01. It was 1, and then it became 1.01, and blah, blah, blah. What did it change by? Roughly 0.01. Did it change by exactly 0.01? No, because it was an estimation. Yes? So do you see how this idea behind what we're doing here is exactly the same idea as tangent lines? The bigger the step in x, the less good our approximation is going to be. Okay. It's just it works further if our function is nice, is well behaved. Well behaved just kind of means the derivative doesn't change that much. So like sine of tan x goes crazy. The derivative is changing all the damn time. Holy shit. So that one, I couldn't move very far and be good. Okay, maybe. Yes?
Can they ask us this without giving us both the x and the dx?
That would be impossible. Yeah. I'd have too many unknowns in my differential, yes? So I have 1, 2, 3 things. So they have to give me 2 of them. Yep. You guys okay? You guys alright? Never? Sure you, Jeff? Okay. Here, let's try a simpler function. Let's do all that with a simpler function. Yeah, and then we'll take a break. Can you guys figure out, don't say anything out loud, figure out the differential for that. Figure out the differential.
Like what you just did, right?
Totally. Oh yeah, this time I could use the solution. So in general, the differential is, and I desperately want you guys to, dy dx is f prime of x. So in general, the differential is just multiply the dx up. Ooh. But you see how this is now a little more straightforward? How much is y changed? Is the slope at the point times how much x changes. This is an approximation because the instant I move from that point, the slope changes. So this is assuming the slope stayed the same. And that's a huge assumption to make. Will I still get a good approximation? Well, as long as I don't move too much, I'll get a decent approximation. So the only thing I have to figure out to finish this differential is what is f prime? What is f prime? 6x, holy shit. Now, let's say x is 1 and dx is 0.02. Can you figure out the differential? What is the, what's your estimate for how much y changes? What'd you get?
0.
Yeah. Now, here's how we check that shit. And let me use the symbols for this. What is delta y? Oh my god. All my pens are dead. Okay. All my pens. That sounds like you should stop and leave, Jeff. No, shut up. Delta y is f of x plus delta x minus f of x. Now that looks like a bunch of shit. I'm pretty sure that somebody out there is going, what is all that shit? This is just, the change in y is, oh shit, sorry. The change in y is y2 minus y1. Yes, that's all it says. By the way, when I do this, there's this one girl that would freak out whenever I do this. Oh no, I got 30. Okay. Y2 minus y1. That's all that shit is, yes? What do I know? What's x? 1. And what's delta x? Yeah, I'm assuming it's 0.02, so I'm going to change x by 0.02. So I need you to understand, there's always these levels of like, when we write something in general, it's always got to look worse than it actually is in practice. All I'm doing, if I start at 1 and change by 0.02, where did I go? Change by positive 0.02. Start at 1, change by positive 0.02, where do I end up? 1.02, yes? So I'm saying, what's the output at 1.02 minus the output of where I started? That's how much my output's changed. That's all that shit says, yes? I understand this could be trippy. There's a lot going on in it, but all it says is, this guy's output minus the original output. That's how much my output's changed. Whoa. So, now you can use your calculator. What is f of 1.02? Right, just plug a 1.02 into the function, yes? 3 point
1, 2,
1, 2, 1, 2. And what's this?
1, 3.
3. So how much did I actually change by? 0.1212. And how much did we predict we would change by?
1, 12.
Pretty good prediction, yes? Good. That's all that idea is. Now, just to help you a little bit, because it's really funny, there's this weird thing where it's like impossible. Then students do this. Oh, there's no way, and then it's like, oh, that makes sense. Oh, why the hell are we doing that shit? That's so easy. What the hell? This is prepping us for the second big idea in calculus later. This idea of the differential, dy equals stuff dx. That's going to become huge when we do the opposite of differentiation. On that note, let's take a break. Come back at, I don't know, a little past 10 till. 10. Come back at 5 till. 5 till. You gonna fall over? Yes, you are. Poor little guy. Okay, so what'd you guys get for local max? Anybody? Local max, what'd you think?
A, C, and E.
Say again?
A, C, and E.
Okay, so let me write this down. A, C, E. Now here's why A and E aren't. I agree with you that A and E are both some kind of highest point, according to the function. Why is C a local maximum?
Is this in between the two?
In between what two?
In between A and E, so it's kind of
No? Isn't D in between A and E?
true.
Is D a max? No. So why is C a local max? So here's the right way to look at it. Locally, the inputs around C, do they end up getting higher or lower than the output at C? The outputs for things near C, do they end up higher or lower than the output at C? Let me say this again. The inputs around C, do they end up higher or lower than the output at C? Lower. So in a neighborhood around C, the outputs are lower than at C. So that's why it's a local, little neighborhood around it, maximum. Can you make a little neighborhood around the endpoints? No. Is that all right? You guys with me? Because what determines this is a maximum is I went up to it, yes? That seems good so far, but afterwards I better go down or else it ain't a max, correct? So here, I'm going up to it. What did I do after this point? You can't even say nothing. It's just not even that it doesn't exist. It's not even like a blank space. It's what if there was nothing, not even a blank space. Trippy. Keeps you up at night. Don't think about it. You guys kind of with me? So the idea of local maximum is literally in the local neighborhood around that, and you can't create one of those at the endpoints. Okay. So the only local maximum is C. Now again, do you understand this is not a quiz? We haven't really officially talked about it. If anybody said A, C, and E, I completely understand why. Now I'm coming in with some formal definitions, yes? A and E. If I was given this and I had never done calculus, I would have said the same damn thing. You're fine. What about local min? Those are more in your face. Local mins. Jeff. I was like, why can't I see? I don't know. Which ones? B and D. Same reason, right? A little neighborhood around B. All the outputs end up higher than at either one, so therefore that's local mins. So this is a local min. Is it the absolute min? No. This is the local max. Is it the absolute max? No. So what is the absolute max? Where does it occur? E. Because that output is the highest output the function reaches. Yes? And of course, what's the absolute min? D. that happened to win that contest too. Yes? So D won out as a local, like it won the local contest, and then it went to nationals and won that one also. Yes? Whereas like B, it won the local contest but lost at nationals. Does that kind of make sense? Maybe? Okay. So you got this idea of local maxes and mins, absolute maxes and mins. For the local maxes and mins, what's true about the slope? It's either 0 or undefined. Because right here, what's the slope? Why is the slope, why is it not differentiable here? What's the slope before that point? Big positive. What immediately after the point it's big negative. So if I graph the derivative, wouldn't it be discontinuous? So it's not differentiable. So anytime you have a kink in your graph, like you literally kinked the garden hose, that's going to be a location of a, it's not differentiable there. But it could be a maximum because it could do like that, or it could be a minimum because it could do like that. You guys kind of with me? What about the other two? Let me introduce this notation, this word, relative extrema. Extreme high, extreme low, we just call them extrema. That's highs and lows. What about the mins, the local mins? What's true about the slope there? 0. So at least with what we've seen so far, and how much have we seen so far? One weird ass graph, Jeff, but if you think about it, is there any way to have a continuous function that has a minimum where the slope is not 0 or undefined? A local min. Could you, a min you would normally think would be like that. That's a minimum. And now we know it could be a kink where it does like this. Yes? Is there any other way to have a minimum, a local minimum, besides those two? Let me just cut to the chase. No. And this kind of gives a feel for it, but that's literally the only places that local mins or maxes could occur. Okay. So the slope was 0 or undefined. Does that relationship hold for the maxes and mins? Absolute. What was the absolute max? E. Is the slope 0? Is the slope undefined? No. There's a definite slope there, yes? You guys kind of with me? And again, this is all kind of a preview. Local mins and maxes can only occur where the slope is 0 or undefined. Absolute, where'd the absolute min happen? Where'd the absolute min happen? At D, at a local min, didn't it? Where the absolute max happened, it happened at an endpoint. So it seems like absolute maxes and mins can either occur at a local, little local hometown made big, or it could happen at an endpoint. Yes? Maybe? Okay. Look at it. So this would be not necessarily. It does for the absolute min, but it did not for the absolute max. Okay. What are the intervals where the function is increasing? Yeah, B to C, D to E. Where is it decreasing? Where is it decreasing? A to B. C to D. See how it kind of filled in what was missing? See how together they fill everything in? Yes? Maybe? No? Screw Jeff? Okay. Do you see? Can you? All right. B to C, that's where it was increasing, correct? So until it gets to C, it's going up. And from C to D, what is it doing? So I'm desperately trying to. All right. This is concept. We're not gonna like do this shit for every problem. Yes? This is just the concept, and then we're gonna formalize it into a method. If I had a function and I see a point where before it my slope was positive and after it my slope is negative, what's probably happening at that point? It's probably a location of a local max. And if I have a point that I'm going down to and going up from, that is a local min, isn't it? You guys with me? Okay. These are all little ideas that are going to come out when we look at the math. Okay. And then I got very, very, very mathy on you. Did you guys try these yet? How do I rewrite F to do this easier? Do it again, sorry. One, good. Now, if I want to find where it has a 0 or undefined slope, now you guys can tell me, what does that mean I'm looking for? Based on what we did in the first part of this worksheet. What is it that could occur at those points? What could occur?
A local min or a local max.
Yes, a local min or a local max. So if I do this process, we saw it makes sense that if the slope is 0 or undefined, that could be a max or a min. So if I'm tasked with finding the maxes and mins, I take the derivative, see where it's 0 or undefined. Let me ask you this question. Can you guys somewhere graph a cubic function for me? Just a real quick sketch. It doesn't have to be perfect. I'll do mine up here. So cubic, it looks like it's going to be a parabola that opens down and then it goes, ha! What do you guys think the slope is right at 0? In fact, you can figure it out, right? What's the derivative of x cubed? 3x squared. So what's the slope of 0? 0. Is that a max or a min at 0? Is there a maximum or a minimum at 0? No, obviously not, correct? It was like, oh, I'm going to turn on it. No, screw it. Oh, shit. So, if I find where the slope is 0 there, it is. That is a possible location of a max or min. So, speaking in terms of slope, why was that not the location of a max or min? Because it was going up to it, and then afterwards, it continued going up. If it wanted to be a max, it would have to go up to it and then go down from it, correct? Okay. Just because the slope at a point is 0 or undefined, it doesn't mean it's a max or min. It actually has to follow that idea of going up and going down, or going down and going up, yes? But how do I find all the possible candidate locations? Get the derivative, set it equals 0, or see where it's undefined. That's all the places where I could get a max or min. Now, in general, does it make sense that if I have a function that represents my profit at a company, that I'd like to know where the maxes and mins occur? What would the max mean? We're making the most money. Yes? And that's what my friend Sean used to do, is figure out the price point for shit so you can maximize that profit. Yes? You're chasing that, ooh, look at this, ooh, that's a nice place. Oh, wait a minute, we want to be there. Right? You know, like, how do we get there? You guys kind of with me? That's boiling business down to that. We want to be there. We're here. Okay, sorry. If you're taking business classes, don't tell your teacher I said that. So coming down here, we're going to make a list of candidate places that could be a max or min. How do I take this guy's derivative? What do I have to do? Product rule. So it's the derivative of this times this plus this times the derivative of this. And what's the derivative of the What's the derivative? 1/2 2x minus 4 negative 1/2 times chain rule 2. Yes? Is that okay? It's to a power, the power goes down by 1. The power comes down, it goes down by 1, and then chain rule says, hey. Now, what am I going to want to do with this? What do I want to do with the derivative? What's it tell me to? Find out where it's 0 or undefined. Yes? Okay. Can you guys all see where it's undefined? What's the only part of that equation that would end up on the bottom? 2x minus 4, yes. Do y'all see that? Do y'all really see that? What's a negative power mean? Flip. So wouldn't the 2x minus 4 then would have to be on the bottom? What makes it 0? Do you guys see what value of x makes it 0? 2. So it's undefined at 2. I need you to see. You can't always do this, but I didn't have to do a lot of work. I could just see it. X equals 2 makes this undefined. That is a possible location of a max or a min. Is the function cool with the number 2? Can I put a 2 into the original function? Totally. But it makes the derivative undefined. Bless you. So let's do this. If I want to see where it's undefined, I can normally kind of see that from the parts that would go on the bottom. So x equals 2, it's going to be undefined. How do I factor this? Because if I want to set this equal to 0, I need to factor it, correct? How the shit do I factor this thing? First off, you see 1/2 times 2 is dead? Yes? Is that cool? Okay. How do I factor this thing? Well, what do they have in common? Those two terms here. Yes, 2x minus 4. By the way, okay, I don't think we've done a problem like this yet. Guys, if I had x squared plus x cubed, how would I factor that? X squared plus x cubed. Why would you take out x squared? Why not x cubed?
Because that's the smallest value.
Yes, you take out the smaller power. Wouldn't you always take out the smaller power? Always. All right, 2x minus 4, what's the smaller power on it? What's the smallest power on it? Negative 1/2. So I'm going to take out 2x minus 4 to the negative 1/2. Why? Because we always take out the smaller power. Now, real quick, I might as well do this. Don't write this down, but just watch. X squared plus x cubed. What would you take out?
X.
And what's left?
X.
Huh?
X plus X.
1 plus 3 minus 2 is 1, yes? 1 plus x to the first. So when you take something with a power out, you subtract that power, correct? I'm overanalyzing this. So this first bit, I had 2x minus 4 to the 1/2, and I took 2x minus 4 to the negative 1/2 out. What do I do with the powers? Subtract, because I'm dividing. Whatever I take something out, I'm dividing it out. And when I divide like basis, I subtract the powers. What's 1/2 minus negative 1/2? 1/2 plus 1/2. Huh? That's true. So I get a full one of these. Plus, what's left here? These killed each other. This was taken out, correct? So all I have left here is an x. Do you all agree with me that that is instantly so much nicer? I took the weird shit out. What's the weirdest shit in here? The negative 1/2 power. Well, okay, if I take that out, I should be left with not so weird shit. Yes?
Wait, so did you just move that x that's on the left-hand side after?
No, I didn't move shit. If I take this out of here, I'm left with this. If I take this out of here, I'm left with that. Right? So I choose what I'm going to take out. Put it down there. What's left here? Bam. What's left here? Bam. So then if I distribute, don't I get exactly what I had?
Yeah.
Okay. And why am I doing this? You're not like, you don't know, man. Remind me why we're doing this? You're like, I don't know. Somebody told me to sign up for this class.
So we can set each one equal to 0.
Set the whole thing to 0, and since we factored the damn thing, almost done. Where's this equal to 0? It's not equal to 0 2, that's where it's undefined, correct? So be really, really careful. It's a negative power. It's not going to make it 0, it's going to make it undefined. But I could see that right now if I wanted to. I could see 2 makes it undefined. Is that cool? Because that negative 1/2, put it on the bottom, that sucks. 0 on the bottom, no good. So x equals 2, it's undefined. When is it 0? When x equals 4/3. Okay. So this would be the first step in a problem that says find the local maxes and mins. The first step is who's even entering the contest. Yes? Who are the candidates? Those are the candidates. The next step would be, well, which of them are actually maxes or mins? Okay, maybe you guys are with me. Because they both could go, no, no. It's like, God, whatever. Okay, maybe. Yes?
When you took the negative 1/2 out of both of them, where's the rest of the 2?
The rest of the 2?
Was 2 minus.
So this divided by this is a whole 2x minus 4. Right?
2.
This divided, so let me put it here.
2 divided.
When I take this out, what's left here is this. What's 1/2 minus negative 1/2? You're the one that told me it's a whole. So this is, I get,
I thought that looked like a 2 in my brain, and I was like, where'd that 2 come from?
and then here, if I take this out, what I'm left with is x.
No, I saw that 2 and thought it was just a normal 2 and didn't see the 1/2 the first one. So I thought it was.
Okay, as long as you can see what it is. I'm not sure what happened. Okay. So, you guys, armed with this knowledge now, if you haven't done part B yet, do it. Sorry. Just make sure you're on the right track. What's the primary rule you're going to use? Uh-oh. Product rule. That's one function times another function. Later, there's going to be a slight chain rule, but I don't have to know that at first. I just have a function times a function, product rule. Be really careful. What's being raised to the 2/5 power, for example? It's x. Yep. If I wanted the 5 in there too, I'd have to put it in parentheses. I thought that's maybe. I heard what you were saying. I'm like, the only chain rule you need is for the 6 minus x, right? 2 comes down in front of it. The derivative inside is -1. Move shit. Alright guys, I'm going to start to catch up to you here. Let's see. This will be, so if I was really being absolutely the most nice to myself I could be, I would do this. So now I've identified for myself the exact things that need work. I apply the product rule without doing derivatives yet. So if you feel like, man, there's too much shit at once, well, don't do it all at once. Write the rule, then do the derivatives it needs. Yes? Because I can just totally focus on 5x to the 2/5. How do you take that guy's derivative? How do you do this derivative?
Multiply the 2 fifths.
Yeah, the 2/5 comes down. 2/5 times 5 is 2. X to the,
-3.
yeah, remember the shortcut I told you guys? 2 minus 5 is -3. Put it back over 5. Okay. So that's done. Plus, what's the root of this guy? The 2 comes down. Sorry?
-1.
Yep. You guys with me out there? I almost hesitate to say this, but do you see if I put the -1 through here, would change that to a positive x, and that would become a -6? Do you guys see that? Listen to this. Never use it if it doesn't make sense. If I see this, I can just immediately make it that. Those are the exact same thing. Those are the exact same thing. Because when I square something, it loses its negative sign if it was negative. Yes? What's 6 minus 4? Squared is 4. What's 4 minus 6? What's 4 minus 6? -2 squared is 4. These both come out the same. Of course they do. Yes? In fact, if you really want to get pedantic about it, take a -1 out. What's negative? I'm Jeff. Take a -1 out. What's -1 squared? 1. So then I just get x minus 6 squared. So they're the same thing. Okay, sorry. Complete side note. Don't worry about it at all if you have no idea what he just said. You're fine. But let me just leave this like this. So this will become 2x to the -3/5, 6 minus x squared plus, minus 10 x to the 2/5, 6 minus x. Is that cool? 5 times 2 times -1, bam. And then stuff, bam. How many terms are in that expression we're looking at now? 2, totally, just 2. There's this crap minus that crap. So look at the numbers. What number can come out? 2. Numbers. 2 and 10, yes? What number can come out? 2. I'm going to move it over here, but this is what I used to always do here. How many x's can I take out? Well, what's the idea when I have powers? I take out the one that has the, we just said it earlier, I take out the one that has the smaller power. And what's the smaller power? That's insane. And then how many 6 minus x's can I take out? Because he can only give 1. That's all nice and good, he can give 2. Yeah, but we only got 1 over there. Okay. Parentheses. So I identified what can come out, and now I just write what's left. I took this guy's 2, I took all of his x's away, and I took one of his 6 minus x's. So what's left? 6 minus x. Yes? So do not let GCF bully you around. We made that shit up. We just look at it, this is going, that's left. Okay. -10 divided by 2. -5. Took -3/5, divided it into x to the 2/5. So 2/5 minus -3/5. 1. So I got 1x, and I took this 6 minus x, yes? Here. Now, the stuff left inside, doesn't that look light years better? Because I took all the weird shit out, yes? And the extra shit out. They both had a 6 minus x. Let me just take that out. So what do I have left in that little, dude, if I simplify this? Become a 5. There. What do I get? 6 minus 6x. And then I could take a 6 out if I really wanted to. Exciting. So, can somebody tell me that poor little negative sign got kind of like absorbed? Okay. Where's this undefined?
0.
At 0. 0 would make this undefined. It would be over 0, correct? So it's undefined at 0. Where is it 0? At 1 and 6. Okay, so those 3 places are potential maxes or mins. Local maxes or mins. Yeah, it's a potential abscess. Yes. Oh, U for undefined, Z for 0. Yeah. You'll see why I did that here in a minute. So we've done stuff like this before. I've had you find the horizontal tangent line, and now it's finally coming home to roost. The only new thing is, where's it undefined? Because now we know kinks are locations of interesting things. Yes? Do it again. Took out the...
The 6, and then.
Oh, here? From here? From here?
Did you factor out?
Yeah, factor 6 out, and then it makes 12 up front, yeah? Yeah.
Oh, because when you take out the 6, you have to multiply it by 2.
Yeah, now I can just propagate it to the front. And everything is multiplication in this expression, correct?
Yeah.
So whatever I take out of one piece multiplies by another piece if it can. Yes. Okay. Do I really need to do that to see? No. But you know, why not? So we now know how to find the points that are places where there might be an max or min. And we all agree that those are important places to find. Yes? So we call those critical numbers. Those are the critical numbers for this function. So up here, these were the critical numbers. And down here, they are critical numbers. So those are the locations of possible maxes or mins. So the next thing we have to do is develop a process to test them. For each one of them, are they a max or a min or neither? This is the little resting place, right? Looks like unemployment is going down. Oh shit! So it looks like maybe it's going to turn in. Okay. All right, so let's see. That's the other side of this. The one with quite a few, like a wall of words. I'm very sorry. Read that on your own time. But the idea is exactly what we saw when we did the graph on the other side. In order to be a max, 2 things. It has to be a critical number, and it must be going up to it and then down from it. Does that make sense? And if it's undefined or 0, if it's going up to it and then coming down from it, it's a freaking max. Yes? And then down if it's a min. You guys kind of with me? What we do is we make this visual. So I think the easiest way to describe what's happening here is just to do it. Can you guys take a minute and figure out this guy's derivative here? Did I turn this on? Who knows? Yes. Yeah, that's true. Okay. Yeah, so I'm going to catch up to you. This derivative is really, really nice, yes? 20x to the 4th minus. Okay. It's almost like past Jeff is trying to be nice to us. Because can you guys see right now, is there anywhere that it's undefined? What kind of function is that? What would you call that? A nice function. Anybody? What kind of function is it? Is it rational? Is it radical? Is it probably some other type of function? Potentially, yeah, polynomial. So this is a polynomial. That means it's defined everywhere. So is there anywhere it's undefined? How can I know, Jeff? No, it's not undefined anywhere. There's no variables on the bottom. There's no value of x that would make this thing undefined. Are you with me? So there's no possible kinks in this thing. 2 half, right? And what's the other location of critical numbers where the derivative is 0? So we ruled out undefined. There's no critical numbers that come from where it's undefined. Now we have to set it equal to 0, and when we do that, we need to factor. Go for it. You start to see, you take a derivative, is it undefined? Where's it equal to 0? You collect all your critical numbers. That's our kind of first step. So this was really nice to factor, yes? What comes out?
Good question.
So then what are my 2 critical numbers? Cool. So here's what we do. We're going to make a number line. And on this number line, I'm going to put my critical numbers. And what I do, not every teacher does this, but it doesn't make sense to me if I don't. Above the numbers, the critical numbers, I'm going to put either a Z or a U. Because it's going to tell future me, after I do a lot of work, what the shit's going on. Both of these get a Z, because they both make it 0, correct? If either one made it undefined, I'll put a little U. So future me goes, oh, thank you, past me. I know what the shit's going on. Yes? So I'm going to put a little Z here and here. Now, here's where things get interesting. I don't give a shit what the number output is. How do I tell if the derivative is, how do I tell if it's going up? If the derivative is positive, how do I tell if it's going down? You're in there, okay. From the, what was the one we talked about? Intermediate value theorem? This is continuous. You all agree with me? It's polynomial. The only way in hell it could be positive and then negative is if it goes through 0. And so what's the only places it could possibly change sign? The derivative could change sign. 0 and 1, correct? So here's what that leads to. You pick any frickin' number above 1. Somebody give me any number above 1. Holy shit. Either get 2 or I get somebody that goes 10 million and 40. All right. If you plug a 2 into the derivative, in fact, it's easier in the factored form. Do you guys see that? Is this, when I put a 2, is this positive? Yes. When I put a 2 in here, is it positive? Do you see how I don't give a shit what the number is? I don't care what the number is. I just have to know, is it going up or down? Yes? So what did we just figure out? When you put a 2, you get positive times positive, which is positive. Could it possibly change from positive to negative anywhere out here? Why not? There's no more zeros. Good. So it's positive forever after that. Somebody pick a number between 0 and 1. That's crazy. 1/2. So when I put a 1/2 into this piece, that is negative or positive? Positive. And when I put a 1/2 here, I get negative times positive is, the middle is negative. And it's negative throughout the whole thing because it can only change signs at the zeros. You're never going to believe. What's a number below 0? What is it? Do it again.
-1.
Beautiful. -1. So when I put a -1 in here, what do I get? A negative, yes. -1 cubed is negative. And when I put a negative here, I get. And what's a negative times a negative? That's insane. So it's positive down here. Let me see if you guys remember. Does anyone remember the idea of multiplicity from pre-calculus? Do you see, I did this whole problem and didn't say a word about it until just now, right? You don't need to know this, but it makes this so much quicker, especially when I have a bunch of shit going on. Do you see how these are both odd powers? There's a 1 here, yes? That means it will change sign around that 0. If I realized that, I only had to do 2. Once I knew that was positive, it changes sign, it changes sign. Do you see if you had like 7 critical numbers? If you just knew the multiplicities? So if one of them, if this would have been a squared, then around 1, it would have stayed the same sign. Do you see what I mean? So do you have to use multiplicities, that idea? No. If you review it or you know it, it makes this kind of problem much clearer. But I don't care which way you do it. Maybe. So what the shit did we just do? What did we figure out? What's happening from negative infinity to 0? It's increasing, correct? And what's happening? So you below this, you could at least do this. It's going up. What's true at 0? Because what is this talking about? What is this exploring? The slope. So at 0, what's it look like? Flat. Yes? Then what's it doing? Going down. Then it's flat. Then it's going up. Do you see how easy it is now to determine where my max and min is? Where's my max?
0.
X equals 0. So when I say where is it, I want the output also. So 0, let me be careful. What is it? So it's at 0, and then what is it? What is the max? 0. And where's the min? So this is a max, and the min would be at 1. And what is the min? Yeah, 4 minus 5, negative 4. Put min there. You guys with me? So it's derivatives, and then this number line thing. And then you can, underneath it, you can make this little picture. And you actually, this is basically what it's going to look like. And it's a 5th power, correct? Doesn't it have any behavior like this from your perspective? Is that right? Yeah, like that. Yes? So it's going to go like this and like that. So that looks like a cubic, but this is a 5th power with not much going on. So it just doesn't turn as much as it could. The fewer, what does x to the 5th look like just by itself? If I graph x to the 5th, you guys know what it looks like? It looks exactly like a cubic. It looks exactly like x cubed. It's just when I add more terms that it does turning points, turning stuff. You guys with me at all? X cubed looks like this, correct? If I have x cubed plus 3x squared minus 5x plus 7, that could look like this shit, yes? The more extra terms besides the highest degree it has, the more wiggle stuff in the middle can happen. A cubed can have at most 2 turning points. So a 5th power can have at most 4 turning points, yes? This one doesn't because it doesn't have a lot of extra terms that make it wiggle in the middle. All right, maybe, Jeff. Okay, beautiful. So let's do this. La la la. We actually made it to where I wanted to be.
No, that's what it is.
So guys, this is the way I would give this to you in a test or a quiz or something. Oh, I'm sorry, did I totally skip you guys? Yeah. Don't take that personal, please. Do you see how that part A? So, from a teacher's perspective, if I didn't tell you what the derivative is supposed to be, and you mess it up, isn't the entire problem gonna be wrong?
Yeah.
So what I'm gonna do is I'm gonna say show, and if you're not able to, you lose points for that one piece, but then you can do the rest of it. You with me? Okay, I like it. I did say one piece, but okay. So you could take a minute and see if you can get this. Here's the trick. This is what sucks about these kind of problems. It is not gonna look like that until you're almost done. So very many times people are on the right track and they're like, it's not looking like that at all. No, it's not gonna look like that until you're done. So if you ever get a problem in the homework that's like, show this, that kinda sucks. Because it might not look like it's supposed to until you're almost done. So just keep going, don't give up. If you can't make it work, go back, come back to it later. Do the rest of the problem, yes? Okay, go for it. Try to show that that's the right derivative. Let's see if Patch Jeff did that correctly. I don't know, we'll find out. Oh, good. I like it. What time? That's insane. Yeah, we'll do that. Okay.
I like it.
I'm going to start doing this. Let's see. Is that right, Jeff? Yeah. I think so. Let's see. Yeah, cool. Oh, kind of skipped a step there or two. Y'all get 10 here? Because you have to have, so the first part's pretty straightforward. The 4 comes down, what do you do? And then here the 5 comes down, but then chain rule says inside 2 comes out, so 5 times 2 is 10. What'd you learn today in calculus? 5 times 2 is 10. And then now we're at the point where I look at the numbers. I can take a 2 out. I look at the x minus 3's. 3 of them can come out. And I look at the 2x plus 3's. 4 of them can come out. Everybody, very often they make a big deal out of this. This is nothing. Look at the numbers. Look at each thing as it comes. How many can you take out in each case? And then I write, now, does everybody see where this came from? Did I even do this right? Let's see. I think I did. Yes, I must have. Yes. So if I took a 2 out, there's a 2 left here, yes? I took all of these out, and I took 4 of these out, so there's 1 of these left. So I'd have a 2 times 2x plus 3 is 4x plus 6. 10 divided by 2 is 5. I'd have 1 of these guys left, right? And I took all 4 of those out, so I'd have 5 times 1 of these is 5x minus 15. Bam. Like terms, and then I could factor a 9 out, put it with the 2. Oh, there we go. Which I think is what it's supposed to be, yes. Could you do that again, Jeff, just faster? Yes. Sorry, so quick. Anybody have any major difficulty doing that, or that's kind of a hard question for people to say yes to? I know. I'm sorry. Can you see their critical numbers? Are there any locations where it's undefined? No, but you must always, never forget, people always get stuck on the 0 thing and they miss things. So make sure, okay, no undefined, now I can focus on where it's 0, yes. All right, keep going, keep going. Look at the numbers. What do we have? What number do we have? Two. Okay, how many x minus 3? 3, good, x minus 3 cubed. How many 2 x cubed? Good, 2 x plus 3 to the 12.
Well, if 4 doesn't flip, that means the 2 ones around it.
And then, what's left?
And you know,
Yes.
2 does flip.
You had 3 of these and you took them all. You had 5 of these and you took 4 of them. So that would be 2 x plus 3.
Yeah, I was going in reverse. And I was
Okay, yes.
You had 5 of these and you took 4 of them. So how many of these are left?
X plus 1.
Good, plus 2 times 2 x plus 3. There's 1 2 x plus 3
Didn't
left.
flip side.
Well, so
Plus.
what you think about is if you were to play it, this doesn't matter.
You had 4 of these, you took 3 of them, so there's how many left? You had 4 of these, you took all of them. So now if you distribute it, you get.
That would be good.
Matter.
Yeah. 4 minus 3.
If you think about this, so from 4, so the power 4 is sitting right here, so these two will be the same. And this is to the 8th degree, so.
It was just a positive.
Positive. And this one is first degree, which is
Yeah,
odd.
that's why
So
we look
flips.
at
This is to the 3rd degree, so it's almost.
So let's see, real quick, what'd you guys get for the critical numbers?
negative 3
Oh,
halves.
it's flipped. Even still.
1 and then 3.
Good, negative 3 halves, 1, 3. You never have to show me where, I mean, hopefully if you have no idea where I got some of these, you'll ask me, but once it's factored, 3 makes that 0, subtract 3, divide by 2, negative 3 halves makes that 0, add 1, 1 makes that 0, yes? Okay. So then I make a sign diagram, and I put in order, dear God. I'll very often have somebody not put them in the right order. I'm like, oh, okay, that's a problem. And over on top of them all, I would put a z, because they each make the derivative 0. You guys fill that in whichever way you want to. And I'm going to do it using multiplicity. Yeah, this should have a place where it's resting. It doesn't actually try to. Poor little thing.
Yes, but. Yes, it's a max, but they're also a max.
Say again? No, we're home. 310 was linear and linear approximations and different.
But I'm right, that's the important part.
That
Well, it's because I ran out.
I don't
this
think
other
it
stuff
matters.
is getting ready to. Where'd it
Oh,
go?
yeah.
Over here. So everything is 4-1 up, yeah.
Okay, wait, so that's.
Oh, you gotta put in 0.
We just have to find.
You gotta put in 0.
Yeah, 0 is 3 to the.
So guys, the way I would do this kind of problem is if I can, I pick 0. Because it's the easiest kind of input to work with. And sure enough, I can pick 0. When would I not be able to pick 0? Is if 0 was a critical number, yes? So if I put a 0 in, I get negative. And in fact, I could do this for myself. If I put a 0 in, I get negative times positive times negative, yes? Negative times positive times negative. Is that cool? And what's negative times positive times negative? Positive. So it's going to be positive in here.
So 2 is
One multiplicity is odd, so it's going to change sign. 3 multiplicity is odd, so it's going to change sign. Negative 3 halves multiplicity is even, so it's going to stay the same sign. So screw plugging a bunch of shit in there. Let me just plug one thing in there. Now, do you have to do what I just did? No. You could pick a number from every interval, plug it in, see what you get. You don't care what the number is, you just care about the sign. So that makes the evaluation very quick if you let it. Could you get the number? Yeah, sure, I don't care. So what's weird about negative 3 halves? Is it going to be a max or a min? It goes up to it and then it goes up away from it. Is that a max or a min? Good. My question is silly. There should be a third option. It's neither, yes? Let's say place where it rests. I'm going to climb. Okay, gotta keep going. So if I put underneath it, it's going to be going up, flat, going up. So it's not a max or a min. Jeff, you got to go further. What at 1 it's flat, and then it's going down, and then at 3 it's flat, and then it's going up. So now I can see my max and my win, sure. That's all I do is win. I can see my max and my min very easily now. Yeah, the max does occur at x equals 1, but what is the max output? What's the max? What is the maximum? Where is the maximum? X equals 1. What is the maximum? Where do I plug 1 in to figure out what the maximum point is, what the maximum output? Yes, so now you start to see. You need to really identify for yourself what f is and what f prime is and use them at the right time. You really understand what I'm saying? So all the stuff we plug, where do we plug in to create that sign diagram? F prime, because we're investigating the slope. Now I want to know where the function is at a certain input. I've got to use the original function, yes? Later this chapter, we're going to bring in the second derivative, and it's going to tell us something about the shape of the graph. So I got to use the right derivative at the right time. Okay. So it's got a max at 1 comma what?
50,000.
So what is it?
50,000.
I like it. So if you plug a 1 in here, you get, where'd it go? Negative 2 to the 4th, so I get 16 times, oh yeah, 6 to the 5th. Holy shit. So 15,000?
50,000.
50?
500.
Okay. In my head, I got Vegeta's going, who's 50,000? That's over 9,000. Okay. And then, where's the minimum? Some of you guys got that, I appreciate it.
X equals 3.
3. This is nice. I'll do this one in my, yeah, 0. Okay. Because when you plug a 3 into the original, you get 0. Okay, I like it. You would, Jeff. So the last thing you need to talk about to really formalize everything we discussed earlier in general in that first sheet we did is how do I get the absolute stuff? Absolute max and min kicks so much ass. The only place an absolute can occur is at the endpoints or at a critical point, critical number. Yes? This is so local mins and maxes, they kind of suck. You have to kind of do the whole sign diagram. You gotta see, oh, they're going up, or is it tricking me? Oh, it tricked you. You know, so you got to do all that. Absolute max and min. Plug in all your critical numbers. Plug in your endpoints. See what's the biggest. See what's the smallest. Done. So absolute max and min kicks a lot of ass. So what are my candidates I have to investigate? I have to know what f of. What are the endpoints here? 0, f of 2, and what is a critical number that's in between those? 1. So do I care about 3? It can't be in my contest because it doesn't meet the requirements, yes? It had to be between 0 and 2, are you guys with me? So you don't have to check every critical number. So I know what f of 1 is. 50,000. What's f of 0? What's f of 0? 3 to the 9th, whatever the hell that is. Let's see, it's 81 times 81 times 3. Do you want it? 65, 61 times 3 is like 19,005 or something. I don't know. I'm probably way wrong. What is
Close.
what?
19,680.
Oh, okay, I can live with that. What we 19,000 something?
683.
And then what's f of 2? 2 will be 7 to the 5th.
16,807.
So what is my absolute min? 807 you said?
Yes.
What's my absolute min? On that interval?
Two X's.
Yes, my absolute min is there. And what's my absolute max? 50,000 is my absolute max out. Where does my absolute max occur? Where does it occur? 1. What is it? What is the max? 50,000. Where is x? What is 1? Yes.
So for the terms that we plug in, we do the 2 that are on the interval and then any critical number.
Any critical number in the
that fall
middle.
between.
Yes. Because if it's a local max or min, it could be the absolute. Maybe it just never gets that far up again. Like we saw in the first picture. There's a local min that was also the absolute min, yes? Or it could be the endpoint. Because those aren't truly maxes or mins. Those are just at the end. So it doesn't go anywhere afterwards, so I can't tell. So I just check all of those. So it's kind of like, it's just a plug in and see who wins. There's 2 contests. Who gets the lowest, who gets the highest. Yes? Okay. So then number 2 just says do everything we just did for this one. And of course, it's a slightly more disgusting function, yes? Yay, Jeff! Let's see. Just to cut to the chase. Well, no, do it. Try to see if you can get the derivative to match up. This isn't that bad of a derivative. Speak for yourself, Jeff. I know. What's the main rule you're using for this? Product. Kicking us. Do you want to talk about that? That's the last one we'll do now. Yeah. So much can I do here? I don't have to do all of them. No. That would be nice, but that would push it true.
Oh, yes, I see what
Check.
So if you take the derivative of, so that first piece is easy, yes, because the x derivative is just 1 times this. Plus x, what's the derivative of e to the negative 2x squared? E to the negative 2x squared times negative 4x. And then they both have an e to the negative 2x squared, so I can factor it out. So then I get 1. This divided by itself is 1. And then I have a minus 4x times x is minus 4x squared. And look at me, I gave myself a little check mark. Hold on. Go, Jeff. Okay. Go, math boy. Go, math boy. Go. Now, here comes a potentially weird question. Is it undefined anywhere? Can you trace out in the air what e to the negative 2x squared looks like? That's actually kind of a big ask. E to the negative 2x squared is a little weird. No. Can you make the exponent on that become positive? All right, this is more than I have to say. Can e become 0? Can e to a power become 0? No. Yes? So this would be 1 over e to the 2x squared, correct? And if I can't make e to the 2x squared 0, it's never undefined, because 1 minus 4x squared is, he's cool, he's a little polynomial, he's cool, you with me? So this is not undefined anywhere, which is bad. Past Jeff, you did bad. You should have gave us an undefined, but I'll be okay. So can this ever equal 0? No. So there's no undefined, and this does not give me any critical numbers because it can't be 0 either. So thanks for showing up. Could this be 0? Hell yes. Okay, go for it. I get 2 critical numbers from that, right? It's the second degree. I should expect 2 answers. So set it equal to 0, and then solve. You get 2 fractional answers, I'll tell you. Let's read it. Yeah, I can do that.
It's not work. Sometimes math work, but it's just correct.
So there's 2 ways to do it, right? You could factor this, set each one equal to 0, you get 1/2 and -1/2, or add 4x squared, divide by 4, you get x squared equals 1/4, take a square root plus or minus 1/2. The danger if you do it this way is you gotta remember the plus or minus, yes? If you ever do a square root, it must be plus or minus, unless some part of the problem tells you it can't be negative or positive, whatever, yes? And this could be anything. Is that, are either one of those ways okay? You can pick the way you like better and do it that way. So now we got our critical numbers. Now we make our, wow! Now something to notice is, can anyone tell me anything about the outputs for this? They are always, the outputs for this. They're always positive. So I can just forget him. Go away, you suck. I can look at this here. So if I put a 1/2 or a -1/2, won't I get the same? I'm sorry, Jeff. Not a 1/2. If I put a 0 in, what do I get? Positive. I get positive, yes. And if I put a 1 in, what do I get? Negative. If I put a -1 in, negative, yes? Because when I square it, becomes +1, so I get 1 minus 4 again. Let me stop for a minute. So before I even do my arrows, can you guys tell where the minimum is? Where's the minimum happen? -1/2, because it went down to it and up from it. That's a minimum, yes? But to be nice to ourselves, there's no reason not to draw a little arrow thing, bam, 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 bam. So I can see that's a minimum, that's a maximum, yes? And then I can plug it in to see what the outputs are. Is that okay? You guys get the flow of that? So all that's going to change in this process is the function I gave you. It could be undefined somewhere, there's slope, it could be 0 somewhere, blah, blah, blah. Okay. So, last thing for today. So, where's my paper? I'm not going to get too deep in this, so don't freak out. There's one problem at least in the homework. Was that one problem, Sarah? I think you were talking to me about it. It was the ellipse, and you had to find the 2 tangent lines.
Yeah, but that wasn't assigned. Like I did it wrong.
All right, I'm still going to use an example. So if I wanted to find, do you all see how there's a tangent line here that goes through that point, if I drew it correctly, and there's a tangent line here that goes through that point? Mm-hmm. If we make that point big? Okay, so that kind of comes up in a few places before now, but today we're going to talk about something a little bit kind of related to this, but different. if I have a function like this, can you guys see, here we go. I don't know if it's gonna show up green or what. If I draw in that line, can you find two places that would have a tangent line that is parallel to that dotted line I just made? Do you see how, wouldn't it be about right here maybe, there's a tangent line that's parallel to this one, do you guys see that? And then like right here maybe, there's a tangent line that's kind of parallel to this line. You guys see what I'm saying? Okay. So within a certain interval, this is still not quite the right idea, but we're slowly getting there. I could have multiple places that have the same slope. Yes, that only kind of makes sense. So I think the way I want to, yes, okay. So let's really, really rein this in. If I live on the interval a to b, and f of a is here, and f of b is here, it doesn't really matter, but I'm just going to plot them there. Make this big. Okay. One key thing I must tell you is that f is continuous and differentiable on the interval a to b. That really restricts things quite a bit. So it's continuous, so it can't teleport, and it's differentiable, so it can't have a kink in it. Yes? Or do any of the other weird shit. So it's gonna be well behaved. Do you all agree that if the function was a straight line, it would have a slope? Ooh, Jeff, getting deep. So if I had a straight line, so as the crow flies, yes? Pretend like that line is straight. Okay. What is the slope of that line? Say m of green. You can do it. You can do it. You can do it. You can do it. Yes. y2 minus y1 over x2 minus x1. Yes? Nothing tricky. Has everybody got this drawn to some degree? And if you don't, you don't have to. I mean, you don't ever have to take notes, I guess. But you should. Now, could everybody connect a and b with a function that is continuous and differentiable, and it could look like anything you wanted to? I've never done this before. Does everybody really understand what I'm saying? I want you to start at A, end at B, and you can connect it with any squiggly line, but it has to be continuous, differentiable. Okay, go. So big guys, if you just draw a straight line, you're like, I did it. Yes, you did, but can you draw something that's not a straight line? So just to show you, it doesn't have to be anything freaky. You could do, did anybody do something like,
Yeah.
sweet, thank you. Do you have a location on your graph whose tangent line would be parallel to this as the crow flies?
Most likely.
No, not most likely.
Yeah.
Definitely, yes? Did anybody else connect them differently? How'd you connect them? Let's see if I can do this again. Can you describe how you connected them? I got you. Hold on. Let me look at you. Go. Like that? Okay, now, can you guys see at least one place where his tangent line would be parallel to the dotted line I drew? In fact, there are 3 places, yes? Do you start to see how there is no way in hell you could connect those with a continuous differentiable function and not have at least one place that's parallel? Because if you start to go away from the line, you have to come back to it, don't you? And so in the middle there, you're going to be parallel. There's just no way to escape it. You guys at all with me? So here, 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 yes? So let's go back to this one. Let's call it, you're not going to believe this, I'm going to call that point C. What is true, okay. what is true at point C? What was the whole thing? What was my whole thing today? It does look like the top of a helicopter, I know. What is true at point C?
Slope is f.
Its slope is the same as this. What symbols would you use to tell me the slope of the function at C? F prime of C. Yes, I think that's what you said. F. So this theorem is called the mean value theorem. And this is section, just so you can play along, 4.2. The mean value theorem says, if I have a function that is continuous and differentiable on an interval, there's at least one location C where the derivative at that point is equal to the straight line slope. And that just, on one level, is like, well, yeah. Because the only way I could escape it is if I could teleport or if I could kink. If I could do one of those two things, I could escape that. But continuous and differentiable, can't do either one of those. Nah. Yes? Oh, sure. I'm sorry. I'll zoom out. What was I doing? I forgot. Oh, it's just, everything's up here. Sorry.
What you said about the mean value.
Yes, the mean value theorem. And it says that if you have a function that is continuous and differentiable on an interval a to b, there's at least one C where this is true. There's at least one number between a and b where that's true, where the derivative at the point is equal to the straight line slope. All right, I'm sorry, that's plenty. So we'll come back. There's one more idea in this section we got to finish, and then we'll do an example of this. What's happening tomorrow? Yes.
Change the section. I want to say it again.
It's 3-9. Yeah, 3-9. Same section.
It was 3.
No, it was 3-9. What do you mean? The quiz tomorrow is 3-9. Yeah.